So right now we have a philosophy about trig functions, that trig functions come from coordinates on the unit circle. And let's go ahead and recall that first on the board. If you start at 1, 0, rotate forward by an angle of theta, then what gives the trig functions? And I just want cosine, sine, and tangent right now. Cosine's given by what? So the x value. I guess that means I better label the point. Cosine is the x value. Sine is. Tangent is. Say louder. Y over x. Nice. So, trigonometry is called trigonometry because it has something to do with triangles. And in fact, it has a lot to do with triangles, and I'm only going to explore one very small facet today. It turns out that trig functions, if you study a right triangle, tell you things about the ratios of the side lengths of this right triangle. Which lets you get lots of good information out of things. And we'll see, I think, a reasonably relevant example in just a few minutes. So let's get started by just even figuring out what should go in these blanks about that. And here's, I think, the right place to begin. This triangle, right triangle, is drawn inside of a unit circle. I guess it goes from 0, 0 on one end to cosine theta, comma sine theta on the other end, that orange thing, and then drop a vertical line, draw a horizontal line. What's the length of the hypotenuse of that triangle? This triangle. Yeah, it's 1, right? That hypotenuse is exactly aligned from the center of a circle of radius 1 to the edge. And let's treat that like it's actually in quadrant 1, just so we don't have to worry about any plus or minus signs. That blue labeled edge, the edge that is adjacent to the angle theta in that triangle, what's the length of that edge? So that's like the x value, right? Which trig function gives you the x value? Cosine theta? Nice. So what's the length of that blue edge? This edge adjacent to theta has length cosine theta. The edge opposite. Sine, right? That vertical edge is exactly the y value. All right, so here's what I'm going to do now. I'm going to take that whole triangle and scale all of the edges up by a factor of h. Still a right triangle? It turns out that's dependent on you walking in the setting of Euclidean geometry, but trigonometry only works in Euclidean geometry. Otherwise, you have to do something else. Anyhow, scale all of these edges up by a factor of h. What's the length of the hypotenuse now? Used to be 1, now it's h. That's why I picked the letter h for the scaling factor, because this way h is the hypotenuse. What's the length of the edge adjacent? Yeah, originally it was cosine theta, but I've scaled it by a factor of h. H times cosine theta is the length of the side adjacent. Length of the side opposite? H times sine theta. All right. So take a look at these two in particular. Do those two in particular, could you solve those for sine and cosine respectively? Yeah, you just need to do some division. So by looking at the second equation, as a consequence of that, what is sine of theta? h. So I see an h multiplied by sine theta, so it looks like I need to divide by it. And it's opposite on the other side, so I guess opposite divide by h. So, the sine of an angle theta is equal to the length of the side opposite that angle divided by the length of the hypotenuse. How much color coding? I think that's plenty of color coding. Opposite divided by hypotenuse gives you sine of theta. How about cosine theta? H times cosine is adjacent, divide both sides by h. So it'll be adjacent divided by h, but h is the length of the hypotenuse. Feel pretty good? And it says here to do something about like writing this down in terms of sine over cosine, but maybe here's a different plan. The tangent's supposed to be the slope of that line, right? By thinking in terms of rise over run, what's the slope of this orange line? How much does it go up? How much does it go right? So tangent is the slope is equal to? There we go. Nice. So there's the trig functions in terms of just ratios on a triangle. And this is useful in a few ways. On the one hand, let's suppose that you want to like determine the height of something, but you don't want to determine the height by having to like climb up it and drop a tape measure or something dumb. If you can measure an angle to the top of that something, and you can figure out some other distance measure, then you can figure out how high that something is. And that's exactly what those surveyors you see walking around with those fun tools on tripods. Those tools measure an angle. Sometimes they'll also measure a distance, but they don't need to. You can do that separately. Another thing that this is useful for is you can study triangles directly and use that to study things about trig functions. So I'm going to put the formulas on the board so we continue to have them. Cosine is adjacent over hypotenuse. Sine is opposite over hypotenuse. Tangent is opposite over adjacent. And on the one hand, like you now know where those formulas come from. Maybe I'll just see a show of hands. How many people already knew those formulas 8 minutes ago when the class started? Cool. Hopefully the justification was at least novel enough. Yeah, that's why these formulas are true. There's a handful of useful mnemonics. Some of them involve rhyming limericks. Some of them are like of questionable taste. I'm an advocate, if you want to remember this via mnemonic. If you can remember the syllables, so, ka, toa, well then you can remember sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So if you can formalize those three syllables, you can reconstruct those formulas for memory. That's useful enough? Nice. And I'll often repeat SOHCAHTOA or whatever it is that I need to do on triangle trigonometry, because it's useful in trying to figure out which trig function you need to use. All right, so let's use this for something more. So here's a right triangle. You don't know what the angle theta is, but could you tell me what all of the trig functions of theta are based on this triangle? Yeah. So I guess the two options are, I could do some stuff or you could just do it. We'll see how people feel. Should I do? Nice. Take a look at that triangle and determine for me cosine theta, sine theta, tangent theta. You might need to start by determining side length h. What's the length of the hypotenuse? Yeah. Oh, that wasn't a handout. We were just telling you the answer. It's 5. Yeah. In fact, here is something, a fact that will come up often enough. There's some color coding. Click the color coding, Chris. 5. This is an example of what's called a Pythagorean triple. If you can find 3 integers with a squared plus b squared equals c squared, that triple is called a Pythagorean triple. 3, 4, 5 is an example of one. There are infinitely many. The next one is like 12, 5, and 14, I think. Check that on the other time. So that's one just remembering. In general, 16 plus 9 is 25, square root is 5, so it doesn't save you that much more. But 3, 4, 5 triangles, if they're right triangles, you can use. All right, is that enough information to tell me cosine theta? So let's see, SOHCAHTOA. Cosine is adjacent over hypotenuse. So what's the cosine of this angle? 3/5. And if you're the type of person who really wants to turn things into decimals, you can. Sine theta? 4/5. And again, if you're the type of person who really wants to turn things into decimals, I guess that's 0.8. Tangent theta?
4/5 divided by 3/5.
But you can do it easier than that. Tangent is opposite divided by adjacent. What's the opposite side length? Adjacent side length? So what you said is correct. It would simplify down to this. But you don't need to pass through that more complicated looking thing. And then again, if you're the type of person who really likes decimals, 1/4. Really? People feeling pretty good about that? So, on the next page, we are going to do an application. I know that I had you do this, but wait, did I? Only in the semester, did I at some point have you compute the dimensions of this classroom? No. Okay. Well, let's compute the dimensions of this classroom. So here's what I've measured right now. Well, let me tell you the plan that I'm going to use. I'm going to stand at the front of the classroom. From my eye level, I am going to look down and measure the angle towards that point at the bottom of the carpet at the back of the room. And I'm going to measure the angle up to the top back corner. I'm going to fill those entries into this diagram. That'll give us some right triangles we can use to just start figuring out distances. If we can compute enough of those distances, we should be able to figure out the length of the opposite wall. Let's try to do exactly that. So, using the tape measure that I brought in, and marking my eye level in chalk, I have measured that distance to be close enough to 69 inches. So my eye level is 69 inches measured just now. You can convert that to feet if you want to, but that's what my tape measure report, so that's what I will use. I certainly wouldn't want to report that in feet, comma, inches. That would make all of the mathematics really annoying. That's basically, I'm not used to walking base 12. I will now measure some angles. I am going to measure the angle down to the bottom of the room and up to the top of the room, and I have a tool that will let me do that. I purchased for myself in the not too distant past at cavity level. Here's what this device has. It's got a little spinny thing to record an angle measure in degrees. Generally, when you're doing some like real world problem, you want to use degrees, or I guess gradients are friendly enough too. It's got a looking tube down there. That looking tube has a mirror in the middle of it, from which you can see a leveling bubble on top. So, I'm going to use this to measure some angles of elevation and decline. Unless someone else wants to do it. So, here's what you're going to do. You're going to look down the looking tube. You're going to, there's a viewfinder in the middle, line it up so that that is right at the bottom of the classroom. And then rotate that little tube on the right of the device until you see the bubble come into focus. Okay, now tell me what angle it says. You have to take it off your eyes to do that. Yeah. And it's in degrees. No, you have to make one more measurement. So far we have recorded that is a 7-degree angle. Now do the same thing, but point it up to the top of the back wall of the classroom. No, you've rotated too far. You've rotated the thingy too far, which is a really easy thing to accidentally do.
Oh, there it is.
So what'd you get?
54.
I mean, yeah, I don't believe that. Yeah, but it has to be you still because the eye level matters. So it has to be the same person making the measurement. Other way.
Oh, there it is. Okay.
Yeah.
So, what if we want a person that's using the...
Yep, we will have to make an eye level measurement.
Okay, got it.
12, that seems more reasonable. And I have to make you do one more thing. I'm going to have you pick up a piece of chalk. I'm going to have you walk up to the classroom and just make a mark with a piece of chalk at exactly your eye level. That'll do. This is easier than me trying to hold up a tape measure to you. All right, so we will reflect on what are some possible sources of error in this technique. I'm recording 65 inches. So here's the game we want to play. Take this diagram, try to figure out other side lengths in this diagram. And our goal is that opposite wall. So I'm going to label some points on this diagram. I'm not very creative, so I'll just go A, B, C, D, E, F. So by looking at this diagram, what is a side length that we have enough information that we could use right triangle trigonometry to log it out? So to use right triangle trigonometry, I need a side length of a triangle, and I need an angle in that triangle. And right now there's only like 2 angles I know, right? I know like these 2 angles and I know that side length. So maybe we should start by trying to figure out, like, is there another angle that we could know? Do we have enough information to figure out that angle? Yeah, how would you do it? How about subtract 7 from 90? So 7 plus that angle is going to be a right angle. Yeah.
Why can't we use
Yeah. So like, because this angle is 90 degrees?
Yeah.
Oh, sure. So that's the right angle in the right triangle. The angle we see in right triangle trigonometry is one of the non-right angles. Like, it's important that there is a right angle here, but it's built into, like it's an assumption before you can use this technique. So, what is this angle? Nice. And everything's in degrees. All right. So Katoa, is there a side length we can now determine? What side length do you see? Give me the endpoints of the side length you could now determine. And maybe as a comment, I don't think I want to find any, I think I can get away without finding any hypotheses. Do we have enough information to figure out that bottom side length from A to B? That's something. It's not the side we want, but if we just keep finding information, eventually, well, there's only so much information in the diagram. If we know all the information in the diagram, then this side length plus that side length is the answer. So, like, let's just find things one at a time. So let's call that side length x. What trig function looks useful if I want to find x? Tangent. Yeah, so let's try it and write down what we get. So it looks like we'll get tangent of 83 degrees is equal to opposite over adjacent. That look like something we could solve for x. And I think I actually want decimal approximations. I want decimal approximations, I think, because this is all very applied. So make sure your calculator is in degree mode, because this trig function is expecting an angle in degrees. Tell me what that side length x is. Anyone not sure how to do it and want me to do it? Okay, cool. Then I can just be patient. And in this case, I really want you to like compare the decimal value with the person next to you, because there is like a really easy mistake to make by accidentally being in degree mode. And presumably not both of you will be accidentally in degree mode. What you get? Say that, Ari.
529.4 inches.
Nice. So there's the approximate value. Does that agree with what other people got? Nice. And I guess to do that, the exact value was like 65 times tangent 83 degrees. And I think we could label some other edges as x too, right? That length is also going to be x because of our rectangle. That length is also going to be x because of our rectangle. All right. So let's just keep on going. Is there another side length whose length you can just know somehow. Maybe I'll suggest this. What's that side length from B to C? 65 inches. Because that's a rectangle. And you know it's a rectangle, well, I guess you're assuming that some angles are right angles, so I guess I'm assuming that the opposite wall is actually vertical, which I don't have the tools on me to check that, but I guess I could have brought in a proper level and just like checked that. Hopefully it's actually a vertical wall. Otherwise, you know, there are other problems. Has that been leaking or is it getting worse? Okay. It is raining out, so it might start leaking at some point. So it looks like the last side that I need to determine is like that side length from D to C. Do I have enough information to determine that? It looks like that's an edge on a triangle. On a right triangle even. From D to C. Maybe I'll call it Y. Do I know an angle in a triangle that involves Y? Yes, that 12 degrees is opposite that, right? So, let's look at that triangle. Do I know a side length on that triangle? Yeah, because I know x. So let's look at that triangle. What trig function looks useful? Tangent again? So let's write down another equation involving tangent. Tangent of what angle do you want to use? Nice. And I'll specify it's in degrees, but I guess it's clear from the problem. Is equal to, tangent is opposite over adjacent. TOA. So tangent is what divided by what? Yeah. And I know what x is, so that means if I can solve that for tangent, I could substitute in the known value for x, then I'd know y. Feel good? All right. Solve that for y and plug in the value you know for x. Yeah.
I did not get the same answer to the question. I don't know if that's my calculator being done or...
Ooh, really quickly ask your calculator what the cosine of 90 is. That'll tell me.
0.
Oh, interesting. Yeah, then your calculator is in degree mode. What'd you get for x?
For 65 times tangent of 83.
Uh-huh.
I got 529.38.
Yeah, that runs to that. 529.4.
Oh, I thought that was a 1.
Oh, okay, no, it's just a, which one do you think looks like a 1?
The 5.
Oh, okay.
I thought you just like scribbled.
I mean, I did, but. All right, we happy? Nope, you're good. Let's use this then. So it looks like I'm going to get y equals x multiplied by tangent 12 degrees. And I know what x is. X is 65 times tangent of 83 degrees. And then I'm going to multiply that by tangent of 12 degrees. That looks like something we could just compute now. And I guess I've got my calculator out, so I may as well. 63 times tangent of 83 degrees times tangent of 12 degrees I'm getting on the order of 109.1 inches. Sure is. That is a good catch. 112.5 inches? Nice. We're going to end with a result that will be suspicious. That's anyone spot any glaring errors so far? All right, so let's use this then. Is this enough that we can now just write down what that length of the opposite side, it'll be the sum of two side lengths? So, I'll use some notation I haven't used in the past. The length of the line from D to B, line on top to indicate it's a line, bars to indicate that it's the length, will now be equal to, let's say approximately, 65 degrees plus y, 112.5, not degrees, this is all inches. And what do you get when you add that up?
177.5.
Cool. That feel pretty okay? Nice. So let's talk about what are some sources of error in this measurement. How accurate do you feel that your ability to use that machine to measure those degrees was?
Probably not that.
Probably not that accurate. Right, whenever I use that, I feel like probably there's a margin of error of like plus or minus at least a degree. And that's like pretty major when you're measuring something like 7 degrees. So there's some pretty big error coming from that. You saw how I was like measuring the height to eye level. How much error do you think was in that measurement? Probably less than an inch, but then it's going to get multiplied by some other big error. So there's some error in that, but let's just see if we trust that. So if I'm, like 6'2", so that's 74 inches. Does that seem reasonable for the height of the room? Okay. So I think I'm more or less. That feel pretty okay?
Do you actually know the size of them?
No, actually, I'm sure I am. I mean, I've done like this exercise a few times, but I don't care what the size of the room is, so. I'm sure you could now like find some sort of building plans that will tell you the dimensions of the room. I don't know where to look for those. But in fact, I tell you what, if you want like an extremely marginal amount of extra credit, go find me a source that has the blueprints for some of these rooms and give me the dimensions by reading those. I don't know where to find them or if they're publicly available, so I might be giving you an impossible task. Oh, here's a more possible task for extra credit. Do people have plans tomorrow, like 5 o'clock? If not, there is a colloquium on voting theory that I'll send an email to you all about. If you attend that, take some notes, come talk to me, you'll get some extra credit. Yeah.
I have a question.
Yeah.
So you're solving for y, you did 65 times the tangent of 83 instead of just the answer that we got for x. Is it okay if we use the answer that we got for x, or should we put it in like that?
Ooh, did you use the decimal value and then multiply that by, did you get basically the same number? Yeah, so the risk in doing that is that you can have rounding errors in the calculator build up. And so that can throw off some things up to the rounding error at the end. But on this problem, like our margin of error was so big that you wouldn't have noticed anyway. So in this one, I think it was fine. It's better practice to use exact values as far in the problem as possible. Nice. All right, people feel pretty good about this application? So what I'm going to do with the rest of today is some more applications, but they'll be theoretical seeming applications. Instead of using the fact that we can have a calculator compute trig functions to now make real-life measurements, I want to kind of do the opposite. I want to use the fact that I can know some facts about triangles to determine trig functions at some inputs. So what I want to do is I want to fill in the remaining entries in this unit circle, at least the ones in quadrant 1, by drawing some triangles. So let's do that. So of all of the entries in quadrant 1 on this unit circle, let's see, we computed trig functions at 0 degrees and at 90 degrees. In doing those, we got cosine of 0 is 1, sine of 0 is 0, tangent of 0 is 0, cosine pi over 2 is 0, sine pi over 2 is 1, tangent pi over 2 is undefined. I'd like to spend today and justify the entries that go in the remaining spaces. And maybe I'll just ask you, so how many people just from memory, as soon as I gave you this unit circle, like filled in all the blanks in that unit circle on the spot? I mean, I could have sworn I saw some people doing that, so it's okay if you did. I'd like to now justify why the entries that you would have put in there are correct. So we're going to start with pi over 4, also known as 45 degrees. And here's the way I'll do it. I'm going to draw a right triangle. For convenience, I am going to set the hypotenuse to have length 1. So I guess this is also a picture in a unit circle, really. I'm going to know that this angle is pi over 4 radians, that this is a right angle, so that means that angle is pi over 2 radians, or 90 degrees. I'm going to label the other sides with some names. The adjacent I'll call A, the opposite I'll call D, because I'm not very creative. That angle that's missing in the triangle, I'll give it a name too, I'll call it alpha. And because, I don't know, have I already used that Greek name for a variable at some point in this class? Probably. If not, that's the Greek letter alpha as typeset by LaTeX. All right, let's study that triangle and just see what things we can know about it. And I think the first thing I want to say is that angle alpha, do you have enough information that you can know what that angle is? What do angles in a triangle have to add up to? This is certainly not something that we mentioned at any point in the class, but probably something you saw in a geometry class. Angles in a triangle have to add up to 180 if you're in degrees. If you're walking in gradients, then I guess they'll add up to 200. If you're walking in radians, then they'll add up to something else. 180 degrees is how many radians? Pi radians. 180 degrees, or pi radians. Which of those two measurements is more suited to this problem? The degree one or the radian one? The other angles are in radians, so unless you want to convert everything to degrees, it's one radians. Oh, cool. So is that enough information that you can find alpha now? I think so. Let's write down the equation that we get by thinking about this fact. Angles in any interior angles of a triangle add up to pi radians. So that means pi over 4 plus pi over 2 plus alpha adds up to pi. Is that enough that you can figure out alpha? Should I do the algebra to do that? Okay. What's alpha? Yeah, let's say about. I hear a pi over 4. Do I hear a second for pi over 4? Nice. And maybe I'll say how to do that even if you don't want to do the subtract things to the other side. Well, if that circle represents all of pi, then there's a pi over 4. Here's a pi over 2, and what's left? A quarter of the pi is left. Yeah. All right, so that angle's pi over 4. This angle's pi over 4. This is now a triangle where two angles are the same. Whenever you have a triangle where two angles are the same, that triangle has some symmetry. It's what's called an isosceles triangle. In an isosceles triangle, the two side lengths opposite those identical angles have to be the same. So that means that the side length opposite this has to be the same as the side length opposite that. So A has to be equal to B. So far so good, we're making progress. And I guess even right now, there's something we can compute. Let's use this right triangle to compute the tangent of pi over 4 because we already can. So let's see. SOHCAHTOA, tangent is what divided by what? Opposite over adjacent. Tangent of pi over 4 is opposite over adjacent. What's the opposite side length? B, I guess? Adjacent is A. Ooh, but B equals A. So that's the same as A over A. Oh, what's A divided by A? 1. I guess as long as A isn't 0, but is it obvious in this picture that A cannot be 0? Yeah, cool. Tangent of pi over 4 is exactly 1. That feel good? Nice. So in this unit circle diagram, I can put a 1 in that space. Angle of pi over 4 corresponds to a tangent of 1. So if I want to figure out sine and cosine, let's think about what we need to do to figure out cosine. Cosine will be adjacent over hypotenuse. Adjacent is A, divided by hypotenuse is 1. So that's the side length A. Looks like I need to actually know what A is. What can I use to figure out what A is now? What's a fact that's true about right triangles I haven't taken advantage of yet? How about Pythagoras' theorem? Side squared plus side squared equals hypotenuse squared. Could we use that to figure out what it is? I hope. Let's write it down and see if it looks promising. So, Pythagoras' theorem says side length squared plus side length squared equals hypotenuse squared. So that'll be A squared plus, well, you know what, if B equals A, no need to write B anymore, plus A squared equals 1. How many unknowns are in that equation? Just the 1? That looks like something you could solve for A. And like, I guess I'll give you the choice, like, I could do it or you could do it. People want me to do the algebra? Cool. So I see like two different A's on the left-hand side, but it's like really superficial. A squared plus A squared is the same thing as 2 times A squared. 2A squared equals 1. Now I only see one instance of the unknown variable. Whenever you get yourself into that situation, you should think to yourself, I want to undo everything I do to A, but in the opposite order. So in this case, you start with A, you square it, then you multiply by 2. I need to undo multiplying by 2 first. What undoes multiplying by 2? Divide by 2? Ooh, so A squared is 1/2. How do I get rid of that squared? Square root. And maybe I'll be like slightly silly right now. I'll put a plus or minus there because whenever you want to do a square, you lose information. Is there a reason A cannot be negative? It's like the picture is in quadrant 1. It's also the side length of a triangle. So unless you have like a convention for what a negative side length would even mean, side length should be positive. Ooh, so we just need to simplify that fraction under a square root? Let's go through the how you do that because I want to get a simpler answer than that. So square root interacts nicely with fractions in that the square root of a fraction is the square root of the numerator divided by square root of denominator. What's the square root of 1? 1. 2 isn't a perfect square, so that's kind of annoying. Is that an answer that I would regard as fully simplified? Nope, it's got a square root in the denominator. How do I fix that? Let's multiply and divide by, how about square root 2? Because that'll make the denominator nice. It'll make the numerator less nice, but I kind of care less if the numerator is less nice. Because dividing by something is the complicated operation there. So make the thing you divide by as simple as possible. 1 times root 2 is root 2. Root 2 times root 2 is root 2 squared is 2. Ooh, so A is just root 2 over 2. Is that enough information that you now know cosine of pi over 4? What is it? It's that side length, so root 2 over 2. Let's also do sine real quick. Sine of pi over 4, yeah, it'll be the same. It'll be opposite A divided by hypotenuse, 1. Oh, that's literally the same. So this will also be root 2 over 2. Nice. We feeling good? Root 2 over 2, root 2 over 2. Looks like I'm running, fill in these blanks. Root 2 over 2, root 2 over 2, 1. So the next thing on the list is to try to do similar analysis for trig functions at these angles. And the analysis is going to be only mildly more complicated. Here's the game I'll play. And I'll sketch out the details now. We won't do it right now because I haven't made it. That looks like a triangle that will let you eventually compute trig functions of pi over 6. Could you figure out that missing angle? Ooh, so whatever that missing angle is, you could also use this triangle to compute trig functions at that missing angle. To now do the walk from there, this triangle is not isosceles, so I can't use the same triangle. But here's a trick I can use. If I copy that triangle and put it right down below it, that'll give me a bigger triangle. That triangle will turn out to be equilateral. That equilateral triangle I will then be able to cover all the side lengths of. Now I'll be able to use SOHCAHTOA to figure out trig functions. So in fact, in the next 23 hours, unless you have big Halloween plans, maybe take a little bit of time, go through the rest of this page, figure out those remaining trig functions, and we will start with this tomorrow. So if you already know it, tomorrow will feel quite light. That is labeled as being extra credit is like 1. Otherwise, I mean, they're mandatory in that not doing them when you're yeah, is there a reason that there's an extra open-ended that should be extra credit?
No, I think it's just
yeah, sure, yeah. That means they're probably something. Oh yeah, that one is extra credit.
Oh.
Yeah. The one that says this is extra credit is extra credit.
Okay.
And I'll get it graded when well, maybe this weekend. Is that one posted to you?
Yeah.
Okay. Then I'll start grading it. So So what I'll do with that is, really that means you retreat any one of the open-ended as extra credit, because I'll just replace the lowest one with that, which is the same as I will now just drop the lowest one off.
Oh, okay.
Yeah.
Thank you.
Yeah.
This might show you the
Ooh, does it have the height? That was not so very different. Okay. Yeah, no, I see that. I've got a tape measure on. They won't be able to tell me the height because it doesn't have like second dimension. Let's see. So 6 inches, every 3/16 of an inch goes to 1 foot. Let's see. Yeah, but I mean, because like all the measurements I made 1 inch, so I don't like
Yeah,
see
no,
it.
the wind, like having a brother not do anything, so the wind was blowing so hard that rain was coming from all directions.
So apparently the depth of the classroom is going to be 4 inches. Do you remember what we got when we did it in class? I remember it being like 12 at some point. It's not a big deal. Oh wow, that's a lot. Let's see, 529, that's like. Yeah. I did think that number seems suspicious.
See if I can find out what I'm sure you have. Usually it's about.
Yeah, I mean, that's it. Whatever the extra credit will not be worth money. So if they ask you for money, then like, well, on to me the thing, then you see that there's a fee to get the thing, and I'll give you the extra credit, and put it in the account.
See the one.
Yeah, see what you find.